Thank you for joining us back on the lead channel. This is a continuation of 3.08, looking at inclines part 2, where I'm going to use some of the things we learned in the last video to apply it to some examples. So I have 3 examples over here. I hopefully will be able to get them done in a timely fashion. So let's get started right away. Let's take a look at our first one. First example is we got an 8 kilogram block sliding down a frictionless inclined plane shown below, and we want to find the acceleration. Answer is provided. So let's draw our free body diagram always on our object. We have the force due to gravity always pointing downwards. We have the normal force pointing 90 degrees away from our inclined surface. That's the first step. The next step, we are going to resolve all our vectors in the x and y components. So we have the x and we have the y over there. We're going to start with the force due to gravity. We have this guy over here, which is our FGY. We have this over here, which is our FGX. And then we know that this is 30 degrees. So as a result, based on our previous video, we also know that due to geometry, this angle here is also 35 degrees. Now, I can also write my FGX and my FGY in terms of their FG, essentially. Now, if you have no idea what to do in a question such as this is always a good step. It's just to resolve your vectors into their components so that you have somewhere to start with. So, based on the previous video, and as well as looking at right triangles, that one being a right triangle, I know that my FGY is equal to my FG times the cosine of theta of 35, because this is the adjacent component of relative to 35 degrees. As for the FGX, this is FG times the other one, which is a sine of 35 degrees. So now I have my components of FG. I am going to try to find the acceleration down the incline. So this is looking at down the incline this way. Notice that we have one of the axes in that direction. So looking at the acceleration on the x, we use F net is equal to mass times acceleration. The only force that is along the x direction is FGX, and this is equal to mass times acceleration. We also know that Fg is equal to mg. So therefore, what we're going to do is, first of all, we know that Fgx is equal to Fg sine 35. So let's substitute that in here right now. This is Fg sine of 35 equals to the mass times acceleration. The next thing is I'm going to take this and I'm going to substitute it in here, which is my mg. Now I have mg sine 35, and that is equal to mass times acceleration. Hey, look at this. The masses cancel out because there's one on both sides of the equation, which means we didn't even need the mass of the block. So I could have easily given this question to you without the mass of the block, and you still should be able to solve the question given the angle of 35 degrees. So let's do it. We have gravity times sine of 35 equals to my acceleration. So let's calculate this out. We have gravity equals 9.81 meters per second squared, and then sine 35, which then I can plug this into my equation, and I should get the answer, which is 5.6 meters per second squared down the incline, or down on the left, 4 directions. Okay, so there you go. This is example number 1. Example number 2, how much force is required to push an 11 kilogram block up the frictionless ramp shown below at constant velocity? That's poorly worded. So we are going to push the block up the ramp at constant velocity. We want to find how much force is required. And the good thing, again, this is a frictionless ramp. Let's draw a free body diagram. We have force due to gravity, always. We have our normal force directed perpendicular away from the away from the surface. We also have a force that is going to push the block up at a constant velocity. So this force is directed upwards, up along the ramp. Okay, so this is this direction over here. We are going to call it FA. We got a free body diagram. Next up, let's break our vectors into our components. We have the x-axis, the y-axis. Hey, look, FA is in the same direction as the x-axis. We don't have to do anything there. However, we got to do something with this gravity. We know that this angle is 58 degrees, making this guy over here also 58 degrees. We have the vertical component of gravity. So we have here FGY. We also have this one over here. Now this is the component of gravity going down the incline, which is our FGX. Based off of this angle and our right triangle, we can now use each of these, use FG to write out the complete expression for each of these force components. So I have FGY equals to FG. Since this is the adjacent side for beside the angle of 58 degrees, this is cosine of 58 degrees. For FGX, this is my opposite end of my angle theta. This is my FG, sine of 58. Sine of 58 degrees. Okay, so now I have done what I've needed to set up my problem. Now what I want to find is how much FA that I need. Now notice something carefully in this question. I want my object to go up the ramp at constant velocity. So yes, my object is moving up the ramp. But because it's moving at constant velocity, and yes, you've guessed it, the acceleration must be 0. So along the x direction, acceleration is 0 meters per second squared. Now, what you could do is you could write out your full F-net equation. If you're like me, I'm kind of lazy, so I will do a little shortcut. But it also makes intuitive sense. Because look at it this way. If I'm going up my ramp, I have two forces. I have FA and I have FGX. Those are the only two forces that are going up and down my incline. Because they are equal and opposite, and my acceleration is 0, that means my FGX component and my FA must be equal. So I can write this simply as my FA must be equal to FGX. That's the only two forces that are going up and down the incline. They oppose each other, and because acceleration is 0, they must be equal and opposite. So let's look at FGX. Let's write everything out. We know that FA is equal to FGX, which is also FG sine 58. Write that out. FG sine 58. Now, I also know that FG is equal to mg. So let's substitute mg in here as well. I have mg times sine of 58 degrees. So I put in my mass. Okay, this one we actually need the mass of the block. 11 kilograms. 11 kilograms times 9.81 meters per second squared times sine of 58 degrees. And after we solve all of this, we should end up with something that's close to or rounded up to 92 newtons. So if you take a look at this question, think about it from a conceptual perspective, there is no friction along this inclined plane. So the only force that you need to counteract is the force due to gravity going down the incline, which will be the enough force for you to push the object up the incline without needing to resist any friction and for it to go at constant speed, which is only the FGX component of the gravity. So it kind of makes a little bit sense in terms of forces. That is example number 2. Let's take a look at example number 3. A box sits on an incline ramp with a coefficient of friction of 0.21. Hey, there's friction involved now. Find the block's acceleration. Alrighty, so let's start with a free body diagram. I have force due to gravity, and I have the normal force directed perpendicularly away from my surface. Now, the direction of friction, be very careful. Now, if my block is going to sit on an incline ramp, and it's probably going to accelerate down the ramp. As a result, if it's going to move in that direction, my force of friction is likely going to oppose that. So I have force of friction directed backwards, up the ramp, to prevent the block sliding down. So now I have my free body diagram. Let's go ahead and analyze our forces. So we have our x component, our x-axis, we have our y-axis, and look, force of friction and Fn both lie on those axes. And again, the only one I have to worry about is the force due to gravity. So we got one component of the force due to gravity, which we have as FGY, which I'm going to write over here, FGY. And then I have this component over here, which I will write here as FGX. I have the angle of my incline, which is 40 degrees, which is the same angle over here based off of geometric analyses. So if again, I'm going to write this using FG. FGY, it is the adjacent side of my angle. So this is FG cosine of 40 degrees. Down over here, I have FGX. FGX is opposite to 40 degrees. So I have FG, opposite side, is sine of 40. Now I have everything set up, and I will have to look at the acceleration of the block down the incline. Now let's take since we want to find the acceleration, we will have to look at along the x direction, along the x-axis. Along the x-axis, we have an F net equals to ma equation. But now we have more than one force along this axis. We no longer have just the f of x, fgx. We also have the force of friction, which is opposing the acceleration down the incline. So my F net equation, the sum of my forces, is actually going to be Fgx, and instead of adding, I'm going to have to subtract force of friction because force of friction opposes my object's acceleration down the incline. And all of this is equal to max. We know that the force of friction is equal to mu times Fn. We don't know the force of friction. Even if we know the mass and the gravity, the angle, we still need to find the force of friction. So we have to find the force of friction using some other method, which is this equation here. So let's substitute force of friction and let's say also force of gravity into this equation over here. If I do that, I am going to have Fg sine 40, which is substituting this guy over here, and minus force of friction, which is also this guy over here, mu Fn, and this is equal to mass times the acceleration down the incline. In fact, I can even change this Fg and make it the mg just to make things maybe even more easier over here. So I'm substituting Fg in here as mg as well. So it looks like we have everything to solve for A except the Fn. Because we have mu. Mu is given to us in the question, and I can write that one out. Mu is 0.21. So how do I get normal force? Well, that's why the y-axis comes in. So now notice that I have to look at both x and y axes to help me solve this problem. I am going to look at my y-axis as a result. So I am going to take the y-axis, and along the y-axis, the object, my box, is probably not going to be jumping up and down relative to my incline. So as a result, my acceleration along that y direction is 0. There's no acceleration of my block along the y-axis, which makes our lives a little easier. Because take a look at the opposing forces. Notice that my normal force is equal to this other force pointing down, which is our FGY. our FGY is our normal force. These are the only two vertical forces. So let's write that down. My Fn is equal to my FGY. Okay? So FGY being FG cos 40, let's write that down too. Fn is equal to FG cosine of 40. And since this is FG, let me substitute my mg in there as well. I get mg is equal to cos of 40. We're getting somewhere now. Because why? We have the normal force. We can now substitute the normal force into our original equation. So, let's do that over here at the bottom. So I'm going to star this. I'm going to star this. We now have mg sine of 40. This is minus mu Fn. But Fn is now mg cos 40. mg cosine 40, which is Fn. And now this is equal, all of this is equal to mass times acceleration along the x-axis. Ooh, look at this. My mass, I have one here, I have one here, and I have one here. If I divide the whole equation by mass, I can get rid of all the masses. Hey, that's pretty good. Because we are now left with AX is equal to gravity times sine 40 minus mu times gravity times cosine 40. If we substitute everything in, we should be able to find our acceleration. Our gravity, 9.81. Sine 40 minus mu. And mu in our equation is 0.21 times gravity and cosine 40. And this one gives us a grand total of 4.7 meters per second squared down on the right. So that is looking at our incline from not just from the x component along the incline, but also along the y-axis as well. So here are the three examples that we apply the free body diagram of our inclines to looking at these questions. Now notice that even in question 3, we didn't even need the mass of the block because the mass canceled out at the very end. This is also a good technique when you're problem solving, is to substitute in your values at the very end. In between, try to use as much algebra as you can because you'll never know when something will surprise you with some of the symbols. So hopefully you enjoyed this video, and unfortunately hopefully it wasn't too long, but hopefully you stay tuned and check out what happens if you have two masses tied with a string hung on a pulley while applied to an incline. That's going to be the next video for part 3. Hopefully you enjoyed this video and stay tuned to next time.